got one already?
Let's
Like the formula.
write down the important steps, and then while you're working on problems, I'll print this off so that you can have this.
Weird. On the other PowerPoint, it's
That's pretty nice.
Print it, I will make you a copy.
Okay.
Okay, so I'll read out the problem, but it's very similar to a problem you're going to be working with on your homework. So I would, personally, if I were taking notes on this, I would write down the values that the problem gives, and then write down the word for it, so you don't have to write down this huge problem. Because it's very similar to a problem you're going to be working with on your homework. So a bike tire has a volume of 900 cubic centimeters. The temperature is 294 Kelvin. The pressure is 200 kilopascals. The tire is too flat to ride, so it needs to be pumped up. How many moles of air must be pumped into the tire to increase its pressure to 250 kilopascals, given the temperature and volume are constant? So, like all the problems we're going to be doing, we're just going to start by writing down the formula we're going to use. EV equals nRT. Or, yeah, you can take a picture of this too, like Marciano's doing this morning. And then,
KPA is pressure, right?
yep, kilopascal pressure. And then since we want to find how many moles, we're going to use this formula. This is N1 equals P1V over RT. And then I wrote N1 and P1 because in this problem there's two different pressures and moles. Because you start out with a certain amount of moles and then you pump more air in. So there's more moles after you pump air in. Just remember from yesterday.
So P initial is...
Yep. So P initial will be 200 kilopascals, and then we need to solve for this N1, the initial amount of moles. And then I wrote on here all the different formulas that you could use depending on what you're solving for. Or if you're pretty confident in your algebra, you can just write this one and then manipulate it however you need to. But it might be helpful to just have all these. So from this step to this step, we just plugged in the values that were given in the problem. So P1 is this initial pressure, that's 200 kilopascals, and then the volume is 900 centimeters cubed. And I didn't have to change those units because the unit of R that we're using is kilopascals centimeters cubed. So we were okay there. And then R, 8.3 times 10 to the third kilopascals centimeters cubed, and then this temperature. And the temperature stays the same throughout the whole problem, so I just wrote T instead of writing T1 or T2.
T equals 294, right?
Yeah. T equals what? It is 294.
That's a different K?
That's a different K. What do you
That's
mean?
the other K.
Oh, 294 Kelvin. Yeah.
Oh,
That's
okay.
what that K is. Sorry. So then after plugging this into my calculator, I got 0.07 moles. And then if I wanted that answer in molecules, I would just multiply this number by 6.02 times 10 to the 23rd. But the problem's asking for moles, so I can just leave it like this.
Wait, 6. Oh, never mind.
Yeah, I was just saying if the problem had asked you to find molecules, then you would just multiply this by Avogadro's number. So this is our initial amount of moles before air is pumped in, but now we need to find the moles after the air is pumped in. So for that, I'm going to write N2 just so I can kind of practice some good bookkeeping and keep these in check. So N2 is P2V divided by RT because we want to increase this pressure to 250 kilopascals, so we need a new label for it because it's different than the initial pressure. So I wrote P2. And then B and T stay the same because the temperature and volume remain constant throughout the problem. Does that make sense why I used N1, N2, and then P1, P2? And then the T and V stay the same? Kind of, so then from here to here, I just plugged in the values from the problem. This P2, 250 kilopascals because the pressure increases to that. And then V stays the same, T stays the same, and R stays the same.
Where's the 8 point whatever?
So then after plugging all those in, I get N2 is 0.09. And then for this problem, it wants to know how much air you pumped in, not the final amount of air. So then we take the difference of that. So I do 0.09 minus 0.07. And that's where I get 0.02 moles of gas we pumped in. Yeah. This one? So I started with PV equals nRT, and then I wanted to solve for N. So I wanted to get it by itself. So I divided both sides by RT. So you get PV over RT. And then I wrote all those equations over there too. Anyone have any questions on any of these steps or why we took the difference of moles at the end instead of just taking this final N2? People still writing this down?
Give it to me and write it down where you pass out.
So if you're still writing, don't worry about finishing it all on the slide. Maybe just write a couple of notes to yourself because we're going to pass out these slides to you.
Oh no! When you're writing stuff down, only write down stuff that's like new or things like why certain steps happened and why we're doing the different things. Things that you wouldn't be able to get just from the sheet on itself.
So maybe try to listen to what we're saying rather than focusing on writing down everything that's on the slide. Because we're going to give you all of these. Okay. So now we have a fuel tank which holds 0.25 meters cubed of gas at a temperature of 280 Kelvin and a pressure of 900 kilopascals. What volume would the gas occupy if...
Do you have to always have a very good temperature and algorithm?
You got to yeah. Maybe probably do.
What was the question? You want to compare what?
Kelvin to or Celsius to Kelvin. And yeah, you do.
That's unfortunate. You didn't freeze it.
Yeah, you forgot to freeze it.
No, that was not perfect.
So I'm gonna copy these for you, you don't have to write it all down. Just try to pay attention and listen. Maybe walk through and ask with those guys, walk through cross-mounting units or something like that on the board.
That's good. Oh, yeah, this is the... Okay. So what volume would the gas occupy if it were released into the atmosphere? The temperature is 300 Kelvin and the pressure is 101 kilopascals. So for this problem, these units don't match our common units of R, and I'm just going to write those on the board because when I say common units of R, I imagine not all of you are just running through all your units of R. So I'll just write that on the board.
I imagine most of us don't know what you just said.
Yeah, that's what I write on the board.
At least I know I don't know what you just said.
Well, yeah, Pascal. Okay. So for this problem, we're given meters cubed and kilopascals, and you can see that those two don't match either of these because we have pascals, meters cubed, and then kilopascals centimeters cubed. So what I did is I converted the kilopascals to pascals. So then we had meters cubed to pascals, so then we could use this constant. Does that make sense why I need to convert?
I'm confused.
So right here, we're given a number in meters cubed, and then a pressure in kilopascals, right? So then we need to convert that because we need our constant units to match the units that we're working with in the problem.
What?
So when you've got our equation of dV equals nRT, so Mr. Rush has written out like the different values we might use for R with their different units. We need R when multiplied by the moles and the temperature to have the same units as the pressure multiplied by the volume. So in this case, we have a volume of 0.25, and that's in meters cubed. And our pressure is 900 kilopascals. So the units, when we multiply that pressure with this volume, it would be kilopascals times meters cubed times meters cubed. But over here, what we would have for units is we have the mole and the temperature in Kelvin, canceling out the per like Kelvin per mole on the bottom here. But on top, so then what would be left of the R, like from our two options for that constant? Our two options are either pascals times meters cubed on top or kilopascals times centimeters cubed on top. And so either way, once the moles and the Kelvin cancel, like once those cancel out from this unit, what we have here isn't going to match. So that's the two options. So we have pascals meters cubed here and kilopascals centimeters cubed.
So then you make the 0.25, 25, and then you go right?
Well, it'd be
So when you convert from meters cubed to centimeters cubed, since it's got that cubed unit in there, it would be, instead of going from 0.25 to 25, it would be going from 0.25 to 250,000. Because you multiply by 10 to the 6th, yeah, instead of 100. And I think just because that's such a big number, I think that's why Mr. Rush chose to, instead of converting meters cubed to centimeters cubed, converted kilopascals to pascals, because that one is just multiplied by 1,000, which is slightly easier than multiplying by a million. But either one would work. Just changes which R value you need to use.
So a good way to check that is to do what Mr. Thompson did and just write down the units of the problem they're using and just make sure that they all cancel out when you work it out. And if they don't cancel out, then you need to convert something. So first, it might not be completely clear, but the volume of the gas that we're looking for, that just means how much stuff the gas is, or how many moles the gas is. So we want to use our N equals P1V over RT1, this formula right here. And then again, I wrote P1 and T1 because the pressure and temperature change from the first part of the problem to the second